Let us consider a drop of sufficiently small size so that gravitational effects can be neglected. Let us further assume that the drop is rotating about a fixed axis. If we assume the bulk of the drop to be occupied by an incompressible liquid of constant mass density ρ1, while the drop is surrounded by a fluid of constant mass density ρ2, then the surface sigma, which is the boundary of the drop, satisfies the following differential equation. 2h equals a over 2r squared plus lambda naught, where h is the mean curvature of the surface sigma, r is the distance from point in the surface to the axis of rotation, and lambda naught and a are constants that depend on several parameters. In this video, we will describe all solutions of equation 1, which are cylinders over a planar curve. In order to describe a cylinder, we only need to consider its profile curve, which is the intersection of the cylinder with the xy plane. Before describing the solutions, we point out that every equation in the variables x and y represents a collection of points that usually form a curve. For example, an ellipse, a circle, or a hyperbola. This equation plays an important role in the classification of cylindrical rotating drops. Here are several images of the points described by equation 2. As the images show, for some choices of C, A, and lambda naught, the collection of points may define a smooth connected curve, a connected curve with a cusp point, or a non-connected curve. Here is the theorem we want to show in this video. If we take the profile curve of a cylindrical rotating drop and we make it roll on a horizontal treadmill located as shown, then the center of the profile curve will trace a curve that satisfies equation 2. These images show how the center of a cylindrical rotating drop generates a curve that satisfies the equation 2. Here is another example that shows our interpretation of cylindrical rotating drops. These images show how the center of a cylindrical rotating drop generates a curve that satisfies the equation 2. From this interpretation, we can conclude that the profile curve of every cylindrical drop is bounded, and we can also conclude that every embedded example or properly immersed example is invariant under a group of rotations Zm equal to the integers mod m for some integer m. We have that if we randomly pick a value c, most likely the cylindrical rotating drop generated by the curve that satisfies equation 2 is not going to be properly immersed.